Okay, so welcome everybody to this week's 1W-MINDS seminar. It's my pleasure today to introduce Fushuai Jiang, who's our speaker today. He received his PhD from UC Davis in 2022. His research area is in nonlinear approximation and harmonic and functional analysis. He's currently a Novikov postdoctoral fellow at UMD, and today he'll talk to us about finding a smooth solution to an underdetermined linear system. So please go ahead.
Thank you, Whitney, for the nice introduction. And then thanks. I want to thank the organizer for inviting. And when I got the invitation, Whitney told me that this is kind of a applied math talk, but then I came from a pure math background. But the thing is that I think this topic that I was going to talk about, there are a lot of potentials for applications, which but then some of the technicalities kind of mask the applicability of the situation. So what I want to do today is to really present a kind of like a uniform techniques to treat a large family of problems. And the hope is that maybe somewhere down the line, some of these techniques will become useful for somebody. Okay, and before I get started, this work is joint work with my former PhD advisor, Kevin Luli from UC Davis, and then Kevin O'Neill, who used to be a postdoc at Yale, and then now he is at MITRE. And I believe he also gave a talk here some time ago. Okay, so let's get into the business. Today I want to talk about a solution to a linear system of the form AU equals to B. And the more precise formulation is that you have some kind of topological space. Let's say that it sits in Rn. And then you have a matrix A and B, and then you want to determine if there exists a smooth solution, which is a function U mapping from Rn to Rp, that solves the system AU equals to B at every point in this topological space. The formulation seems pretty simple, and then we have some toy cases. For example, if your matrix A is a square matrix and then is invertible, then there's really not much you can do, right? It is what it is. You can just invert a matrix, and then how smooth the inverse is will determine how smooth you can choose U to be. On the other hand, if the system is overdetermined, it is still kind of, it is what it is situation because it's either inconsistent, or if it's consistent, you can still kind of like invert the system. The interesting case comes in when you try to consider an underdetermined linear system. And in most cases, it's still okay, right? Because you can cook up some kind of pseudo inverse and then try to apply this formula again to do analysis. But the situation becomes really tricky if there's some kind of rank drop, right? So the dimension of the kernel suddenly increase or decrease, and that's really what can mess with the regularity of your solution. So today's talk, we will really just focus on if you have a highly undetermined system and then you potentially have a rank drop situation, how would you handle trying to find a smooth solution to the system? And I want to begin with an example by Epstein and Hofstadter. So these two people, they're algebraic geometers, and they cook up this simple looking linear system. So you have three functions, U1, U2, U3, that are unknown. And then you're given polynomial coefficients, x squared, y squared, and x, y, z squared. And then you have some target function b, depending on x, y, z. So this linear system here is kind of outrageous in a certain sense, because if you're only looking for a continuous solution, it turns out that you already have to start taking derivatives, right? So this comes down to some kind of compatibility solution. So if you stare at the system a little bit, you realize that the continuous solution U1, U2, U3 exists if and only if it satisfies some kind of compatibility condition in terms of, if you take a derivatives on a certain set, you have to, the function b has to vanish, right? So think about this as some kind of a Frobenius theorem, right? So this phenomenon is kind of curious because, we are looking for a continuous solution to the system, but then we have to take derivatives. And the situation becomes even trickier because the starting assumption is that we just want you just have a topological space E. You don't know if you have any differentiable structure. Or actually, you don't know if you have any structure at all other than it being closed. So we have to keep in mind what to do when the underlying base set does not have a reasonable structure for us to take derivatives. And that will be an echoing theme for the rest of the talk. All right, so this is the linear system that we're trying to solve, AU equals to B. This question actually first come from the algebraic geometry community, posed by Brenner, Hofster, Kolar, and Epstein. And Kolar is the first person to consider continuous closure of differential ideals. And it turns out that this particular problem, or maybe the steps to solve this problem, is related to problems in control theory and optimization, and maybe probably a lot of applications to trying to solve a linear system. So I'll just refrain myself from speaking more. Okay, so this is the problem that we want to solve in the most general form. So we have a compact subset of Rn, and then we have some given data A that takes a point in the compact set E into some vector Rp, and then another vector value function taking E to Rq. And the question is that how can we decide if there exists a matrix value function U such that you can solve the system AU equals to B in a certain sense. So here I want to list a couple of progress in terms of Whitney techniques, right? So Kolar and Fefferman were the first group that consider the problem with the C0 coefficients, C0 regularity, but with polynomial coefficients. And then a couple of years later, Fefferman and Luli considered the whole system for Cn. And then in 2019, they also considered a system where the given coefficients are semi-algebraic sets. And the problem that I want to consider has a little bit more constraint. So I called it a generalized Brenner-Epstein-Hofster-Kolar problem. So besides the given data A and B, I also put in a constraint function which I call omega. So omega will take a point in E and map it into some kind of convex subset in this matrix space. And then the system that I consider may be equality or may be inequality, just to state it in the most general form. So I want to solve AU equals or less or equal to B, subject to the constraint that the matrix has to lie in some kind of convex sets. Right, so this may be useful when, for example, we want the U to have some kind of, say, positivity structure. It has to be a PSD matrix, for example. Right, and then another adjacent work is done by Luli and O'Neill in 2003. So they studied the system with inequality instead. Okay, so let's try to remember this slide. We want to solve a linear system or linear system of inequality subject to some convex constraints. And to do this, I want to complicate my situation a little bit by introducing some more terminologies. I use this script P to denote the vector space of polynomials of degree at least no greater than n in n variables. And then if you have a smooth function phi, which is locally differentiable, m times locally differentiable, I use this script J to denote the mth order Taylor polynomial of this smooth function at the point x naught. So this x, and I'll call this object an mjet. So obviously this mjet is a polynomial. And then if you have a vector value function that is also m times differentiable, you can just apply this jet operator component-wise, and then this will spit out a polynomial vector. All right, and I use this script R with a subscript x naught to denote the ring of mjets at the point x naught. So obviously this ring is isomorphic to the vector space P. And then we want to define a ring structure as follows. So this funny little product is defined as follows. So if you have two ring elements, R1 and R2, so these are polynomials of degree at most n. So when you multiply them, and of course the degree will not necessarily be less or equal to n, right? It can be 2n at most. So what you do is that you truncate it by taking the jets again at x naught. So this guarantees that the multiplication lies inside the ring of n jets. And similarly, if I put an arrow on top, I denote this by the, if I put an arrow on top, this becomes a Rx module of n jets. So this is, of course, isomorphic to d copies of the polynomial vector space. And the action is defined similarly. So if you have a ring and then you have a vector of polynomials, you just define a ring operation component-wise. Right? So under this operation, it becomes a R module. And the reason why I want to introduce all these terminologies is to introduce the following definitions. So this definition is kind of a very heavy abuse of terminology. So just please bear with me. So if you have a subset of subset E of Rn, I say that gamma is a bundle over E if gamma consists of families of subsets of the Rx module. And then all of these subsets are parameterized by the points in E. And I also allow these subsets to be empty if you want it. And I call each gamma of x to be a fiber of this bundle. And then, of course, the fiber is parameterized by the base space E. And a CM section of a bundle is simply a vector value function, capital F, such that at each point, x in E, if you take the Taylor expansion of this function, it lies inside the fiber. So think about this as, for example, a C1 section is essentially just, a CM section of a vector bundle is essentially a m times differentiable vector field, right? So here you're just expanding it in more terms, in terms of Taylor polynomials. So it's just a higher order notion of a vector field. Okay, and the problem that I really want to look at is this jet selection problem. So if you have a compact subset of Rn, and then you have a bundle sitting on top of this convex subset, such that this the fiber is a convex subset of the Rx module for each point x and E. And the question I want to ask myself is that how can I tell this bundle has a CM section? Okay. The reason why I want to consider this jet selection problem is that it implies the solution to a linear system. So I'm trying to solve a more general problem. So remember the linear system problem, solving a linear system comes down to solving a U, let's say less or equal to B, such that U is constrained by this omega at each point x and E. So what I can do is that I will design a specialized bundle, and then the fiber of each bundle consists of the following form. So gamma of x, so fix a point x and E. I define the fiber gamma of x to consist of all of the polynomial vectors or matrix value polynomials, such that it solves this linear system at this particular point x, and it satisfies the constraint omega at this particular point x. So the only one point constraint and one point solution, nothing else. Okay, and obviously this is a convex subset of the Rx module, right? Because all of the constraints here are convex. Now, if we look at a section of this particular specialized bundle, it by definition, it is a matrix value function such that the Taylor expansion of each at each point belongs to this particular fiber. Now, if you unravel the definitions of what it means for the Taylor polynomial to lie inside this particular fiber, it means that for every single point x and E, ax dotted with f of x, well, f of x is the value of the function at that point, right? And the value is just a constant term in the Taylor expansion, right? So a times f is the same as a times the jet of f at x. And then this has to lie inside a constraint because I'm selecting from this fiber. And on the other hand, A times F will solve the linear system as well, right? Okay, and which means that a section of this particular fiber is a solution for the linear system. Okay, and it turns out that this particular jet selection formulation is even more general than that because it can deal with a lot of problems that potentially have different flavors. So I want to bring out the second problem that the jet selection problem can solve. So this is actually the starting point of my dissertation research, which is the Whitney extension problem posed by Whitney maybe close to 100 years ago, 90 years ago, right? So the original problem states that if you are given a compact subset in Rn and then a continuous data on this compact subset, and Whitney asked, how can we tell if there exists a smooth function that extends this continuous data? And the progress for Whitney's problem is historically has been very sparse until the past 20 years or so. So it was first posed by Whitney, and then he solved the problem in one dimension. And then 30 years later, Glaeser solved it in Rn, but then the regularity is C1 only. And then in the early 2000s, there's another progress by Bruni and Schwarzman in terms of finiteness principle, which we won't talk about today. And then there are some algebraic techniques by Bierstrom, Millman, and Pawłowski in 2003. And then the full solution is obtained by Fefferman in a series of paper about 20 years ago. And then he used this particular technique called Glaeser refinement, which we will revisit at the very shortly. Okay, and it doesn't, it solves the Whitney extension problem. The jet selection problem will solve the Whitney extension problem, but it actually solves a more general version of a Whitney extension problem. So it's Whitney extension with constraints. So the setting is that if you're, again, given some continuous function on a compact set, and then you're also given two obstacle functions. Let's call it L and U, L for lower and U for upper. And the question is kind of the same, like how can you tell if there exists a smooth function that agrees with this little continuous data on E, and moreover, this F has to be upper bound, lower bounded and upper bounded by the two constraint functions. Right? So if you think about this in this PDE scenario, you're essentially looking at an obstacle problem, and then, for example, looking for trying to solve the Laplacian U equals to 0, it comes down to trying to find a minimizer for the H1 norm. Right? Okay, so this is closely connected with the obstacle problem in PDE. Right, so how do we solve the constraint extension problem using the jet selection problem? Right, so this is a constraint extension problem. And then, again, as before, we build a specialized fiber associated with the given data. So the given data is phi, L, and U. So I cook up a fiber such that at each point, this fiber consists of just scalar value polynomials, such that whenever there's data, I force the polynomial to agree with phi of x. And when there's no data, I just force the polynomial's value to be inside our constraints. Okay, and this is again a convex fiber because either it is just a singleton, either it is just an affine fiber or it is a cylinder, right, defined by this constraint. And then if you think about it, a CM section of this particular bundle is just a smooth function such that the Taylor expansion is the evaluation of the Taylor expansion at the point x is either the given data phi of x whenever there is data, or it has to obey the constraint L and U when there's no data. And in particular, as before, the evaluation of the Taylor expansion is just the constant term, which is just the function value. So the section F has to agree with phi on E, and then it has to be squeezed between L and U everywhere. Okay. And in particular, this section here is a smooth, is an extension. Sorry, the section here is a solution to the extension problem. And it turns out that I can solve a third problem using the jet selection techniques. And this third problem is kind of a generalization of the constraint extension problem. And to do this, I want to reiterate the terminology, right? So I write this convex subset of RD to denote the collection of closed convex subsets of RD, as the name suggests. And I allow it to be empty occasionally. And the set value function, capital Phi, is just a correspondence, right? So for each point x, it maps to a particular set that is closed and convex and possibly empty. And the third problem that you can solve is the convex selection problem, which is a generalization of the constraint extension problem. So here the setting is that you have, again, a compact subset of Rn, and then you have a set value function such that the correspondence is closed and convex and possibly empty. And the question is that how can you tell whether there exists a smooth solution such that it jumps through all of these convex subsets? And so I believe I am kind of the youngest person among all the audience, but even I remember, you know, in the Nokia phone, you have the little helicopter game where you try to jump through all of the obstacles. Right? And here, K of X plays the role of the region that you can jump through, and then you try to find a trajectory as smooth as possible throughout all of these little hoops. And the reason why this is a generalization of the constraint extension problem is that, well, to find an extension, you just force the K of X to be a singleton. And here it may not, right? It can be a whole region with error. And this problem is associated with a problem in control theory where you look at differential inclusion, right? So if you look at a derivative of some kind of system, it has to lie inside some control set K of X. And if you look at C0 instead of Cm, you are kind of in the regime of the continuous Michael selection problem. And to see that how the jet selection problem solves the convex selection problem, we do the following. As before, we cook up a special fiber. So here, the fiber is associated with a set value function k. Right? So for each point x, I cook up the fiber such that it consists of all of the polynomial vectors, such that if you evaluate that vector at that particular point x, it lies inside our convex set k. And then a CM section of this particular bundle, well, that is just a vector value function such that the Taylor expansion lies inside this fiber. And as before, that just means that the function value, which is a vector, lies inside this convex set, right? So a CM section of a bundle is a solution to the convex selection problem. And at this point, I should be able to convince you that the heart of the matter is to solve the jet selection problem, which is to say, so you have a compact subset, and then you have some kind of bundle, such that the fiber of each bundle is a convex subset of this module, this R module. And the question is, how can you tell if this bundle has a section? Okay, so right now, what have I done? Close to nothing, right? I have turned a problem that was, you know, solving a linear system into something that is almost completely unrecognizable. And I also haven't made the problem easier. I made it more abstract, but if you really think about it, trying to extract a section from a jet bundle is as hard as solving a PDE. And if you're solving a PDE, you can just, you know, prescribe your partial derivatives to satisfy some constraints. And this is exactly kind of the regime we're in. So the only reason that we want to turn this you know, a simple linear system into this general formulation is to use this very big hammer called Glaeser refinement that Fefferman used in his solution to the Whitney extension problem. So well, before I introduce Glaeser refinement, are there any questions so far? Well, if not, let's talk about what a Glaeser refinement is. Well, to motivate things a little bit, I want to start with a very classical theorem, Taylor's theorem. Well, Taylor's theorem says that essentially it's like a higher order Lifshitz compatibility condition, right? So if you look at the Taylor expansion of a smooth function at different points, they satisfy this kind of higher order Lifshitz condition, and then the Lifshitz constant is replaced by the CM norm. And moreover, if you look at the Taylor expansion at 2 points, um, and if the 2 points start to get really close, then the Taylor expansion gets really close as well, right? So um, yeah. And it turns out that there is a partial converse to the Taylor's theorem, and that's called the Whitney extension theorem. So Whitney extension theorem says the following. So if you have a whole bunch of polynomials, which I'll call the field of M jets, which is polynomials parameterized by points inside whatever space, whatever base space you start with. And Taylor's theorem says that if all of these polynomials they satisfies the conclusion of the Taylor's theorem, meaning that if the polynomials get close to each other as the base points get close to each other, and moreover, if they satisfy this like higher order Lifshitz condition, then it turns out that you can explicitly reconstruct a smooth function that take these polynomials as their Taylor expansion. Right, so this kind of correspondence, the takeaway for this correspondence is that how smooth a function is can be boiled down to how well you can approximate it by polynomials, i.e. Taylor polynomials. Okay, and that is a great news because smooth functions can be hard to work with. Well, I'm not saying that polynomials are easy to work with, but then we have more tools to deal with polynomials, and they have a more rigid structure. Okay, so with these in mind, we move on to the definition of a Glaeser refinement. So we fix a bundle gamma, and the base space is E, and we fix a number that only depends on the dimension and the smoothness. So the zero stage of the Glaeser refinement of this bundle is just the bundle itself. Now, let's fix some number L greater or equal to 1. And the Glaeser refinement essentially does the following. So every jet in the Lth stage of the Glaeser refinement is an iterated limit of the jets in the previous stage. And I highlighted this iterated limit because it is not quite the limit that we're used to. And the reason is because of this following phenomenon that we may have encountered in undergrad real analysis, right? So what do we know about the relationship between existence of directional derivatives and total differentiability? Well, total differentiability implies the existence of directional derivatives, but not the other way around, right? And if we just take limits in the usual sense, then we only get directional derivatives. We may lose total differentiability. So we have to be careful about how we take limits of in higher dimension. Okay, so the precise definition is a delta epsilon definition. So fix a polynomial P naught in the L minus first stage of the Glaeser refinement at the base point x naught. And we say that this P naught survives the next stage of the Glaeser refinement, namely P naught will be passed on to the Lth stage of the fiber at x naught. If and only if, given some little tolerance epsilon, there exists a delta neighborhood, such that every time you choose k number of points in this delta neighborhood around x naught, you can find polynomials pi from the L minus first stage of the fiber at xi, such that all of these polynomials are compatible with error epsilon. So this is a stronger condition than the usual limit in the following sense. So all of the PIs, they have to converge to P naught. But moreover, all of the PIs, they have to converge to each other. And hence, I highlighted for all 0 less or equal to ij less or equal to k. Right? So not only the PIs have to be friends with P naught, the PIs all have to be friends with each other. And hence the notion of iterated limits. Okay, so why is this a reasonable tool to look at? So let's first do a sanity check. Recall that Taylor's theorem says that if you have a smooth function, then for epsilon bigger than 0, there exists some delta such that the Taylor expansions are epsilon close whenever x and y are delta close. So this is unpacking the little o definition, little o condition in Taylor's theorem. Well, Glaeser refinement says that there is for epsilon bigger than 0, there exists some delta such that all of these PIs they are epsilon close. Well, if you actually have a solution, if you actually have a section, and then you take the polynomials to be the Taylor expansion of your section, right? So you just replace p sub I by the jet of f at x, p sub j by the jet of f at y. You see that the first displayed equation would imply the second equation. And this is to say that because of Taylor's theorem, Glaeser refinement does not lose true solutions. And that is great news because I don't want to, feed my fiber into this machinery and then somewhere in the middle I start to lose solutions to my problem. So that is the first great news. And the second great news is, well, before the second great news, I want to introduce another definition. So we say a bundle is Glaeser stable. If you hit it with the Glaeser refinement machinery, it doesn't change anymore. So if you apply GR to each fiber, it stays the same. And why is Glaeser stability a good notion to look at? So recall Glaeser's condition. So we want the PIs and the PJs to be epsilon close whenever all of these points are in the delta ball. Okay, and the reason why we want to look at Glaeser stability is actually because of Whitney extension theorem. So recall that the original statement of the Whitney extension theorem says that if the jets are close in the little o sense, then you can construct a CM function that takes these polynomials as their jets. But you can actually translate Whitney extension theorem into Glaeser's language. So if you cook up a bundle such that this is a pretty silly bundle, so such that the fiber of this bundle at each point is just a singleton. It's just a px from the Whitney extension theorem. Then you can restate the conclusion of the Whitney extension theorem as follows. So the field of m-jets, it extends to a smooth function if and only if gamma is Glaeser stable. And this again comes down to the correspondence between this delta epsilon for Glaeser's condition and Taylor's theorem. So all of this will suggest that we should be looking for solutions in the Glaeser stable bundle because that's where the true solution will lie. But before we get ahead of ourselves, we want another sanity check. And the Glaeser stability turns out to be a very good notion for the following reason. So it turns out that you can, every time you're given a bundle, you can turn it into a Glaeser stable bundle in the following instance. So the theorem that we proved is that there exists some number such that if you Glaeser refine many times, the number of times that you Glaeser refine exceed this number, then your fiber doesn't change anymore, right? And this is great because it already offers us a partial solution to our problem, right? So if any stage the Glaeser refinement results in an empty fiber, then this bundle can have no section. You have no polynomial to choose from, and then you're done. And this is because the Glaeser refinement does not lose any true solution. Okay, and let's look a little bit at the stabilization just to convince you that this is kind of the case. right? So previously, in Fefferman solution in Fefferman solution to the Whitney extension problem, the fiber here is actually a coset of a submodule. And he showed that if that's the case, then all of these fibers will stabilize, right? So think of a submodule as just a vector space. And the Glaeser refinement is actually a linear procedure. So every time it kills a single polynomial, it'll kill the span of that whole polynomial. So a whole dimension will be gone, right? So the trimming of Glaeser refinement happens on the dimensional level. And here we don't have the luxury of a linear subspace. We have a convex set. And we show that even if that's the case, the Glaeser refinement still stabilizes. And the question we really want to ask ourselves is that what if this trimming happens on an infinite dimensional level, right? So, sorry, infinitesimal level, in that maybe the Glaeser refinement will, the fiber on the Glaeser refinement will try to converge to some shape, but it will never get there. And it turns out that that does not happen. And the solution is actually to look at a correct notion of a dimension. So if you have a if you have a polynomial vector p, and then I define this like local notion of dimension to be the following. So it's either the dimension of the face of p, sorry, the face containing p, if p is actually a member of this fiber. Otherwise, I just define it to be negative infinity. It doesn't really matter. And any negative number will do. Right, so what is this dimension of the face? Well, I think this picture will say nicer, right? So if you have, say, this wedge over here, if P is actually in the relative interior, then it just the dimension, the local dimension of P is just the dimension of this convex set. On the other hand, if it's in a straight boundary, say over here, then the dimension of P is 1 over here, right? Because here you can think of, if you really zoom in, you just have a linear subspace. You cannot see anything else. On the other hand, if you encounter some kind of corner, then we define the dimension to be 0. And on the other hand, if you have any curvature present, we also define the dimension to be 0 in this case. Right? And this local notion of dimension is great because it actually tells us something about the membership, right? So if you look at the first bullet point, this dimension of P is greater or equal to 0 if and only if P is actually a member of this fiber, right? So if the dimension of P stabilizes with respect to this fiber, then P is either a permanent member or it's bound for life, which means that it gets shoved to negative infinity. And what we're able to show is that this special notion of the dimension was stabilized, and hence the membership of every single polynomial in this fiber will stabilize. Okay, so this is great news. This is because if you're given a fiber, I can just crank this Glaeser refinement machinery until it stabilizes, and then we might as well just start looking at solutions from the Glaeser stable bundle. So the heart of the matter, the new heart of the matter becomes the following. So if you have a compact subset and then you have a bundle, and you also assume it to be Glaeser stable. And the question is the same as before, can you tell this Glaeser stable bundle have a section? And the big theorem that we prove is yes. Yes, we can tell. And moreover, we have a pretty nice result saying that every element in this Glaeser stable bundle comes from a section. So you have thrown away all of the junk and you have kept all of the true solution. Right? So this is very great news. You may be able to realize that there are a lot of white space over here, and that is because, it's yeah, that is because it's sometimes you just need to put extra conditions. Like life is not perfect. So yes, if gamma satisfies some mild conditions, and the some imprecise statements about the mild conditions are as follows. So the first mild condition is that if you look at the symmetric difference of the fiber gamma, it looks like a submodule. And this is actually not a hard condition to check, and it's a somewhat natural condition because if you think about it in terms of the linear system, right? So gamma is built from the solution set of the linear system. And then if you look at gamma minus gamma, you're essentially looking at a homogeneous solution. So you're just looking at the kernel of your data matrix, and that itself is an ideal, right? And then in this case, we're looking at vector value stuff. So we're looking at submodule. And mild condition number two is I don't know if it's out of necessity, but it definitely helps analysts do things, right? So if the condition is that this gamma emits can be continuously parameterized by both x and m. So I can write gamma as a nesting union of gamma of x comma m, where m sort of denote the notion of the size of the fiber. So think about it in terms of like the ball. So think about this number m as like a number that controls the size of the coefficients of the polynomial. Right? So it's all nesting within each other. And we require the shape of the fiber is kind of in more or less notion continuous in both the base point x as well as the new parameter n. Okay, and we are ready to describe the solution to the jet selection problem. Right? So you start with a bundle, you check gamma for the mild conditions, and you glaze, and if satisfied the mild conditions, you can proceed. And it turns out that most of the fibers that we care about, they satisfy these mild conditions. Okay, and after receiving this gamma satisfying the mild conditions, you feed it into this Glaeser refinement machine, and you refine it until it stabilizes. So you have two cases left. Either you end up with some empty fiber, and that case you know that well, there is no solution to be found, or you end up with no empty fiber, and that means that you have a successful story. Every single polynomial from your fiber comes from a true solution, and you can just maybe use, for example, the Whitney extension theorem to reconstruct the solution. Okay, so we have solved the jet selection problem, and therefore we can solve the linear system, right? So you just, as before, you construct a fiber. And then you check that this particular fiber satisfies the mild conditions, and then you can just solve the jet selection problem for this particular bundle consisting of these fibers. And therefore, we can declare victory. Right, and how many time do I have left? 5 minutes?
Um, yeah, I mean like 10 minutes or so.
Let's do 5 minutes. Right. Okay, so I want to talk a little bit about the computation of the Glaeser refinement. Right? So this here is the definition of the Glaeser refinement for your reference. And so how do we compute this? Right? So if you're given some points, say x naught, x1 through xk, and then you have some polynomials, p naught through, sorry, this should be a pk. So all of I should be k, my bad. And then you can define a quadratic form associated with the base points and the polynomial p. And then remember here you have this like epsilon closed condition, right? So you just move the xi minus xj to the other side, and then you just take the square and then you sum it all up. So this will turn this condition into a quadratic form. Right? And the associated optimization problem is really just we want to so given x naught and p naught, we want to minimize this quadratic form subject to the constraint that all of the pi's come from come from other fibers, gamma of xi, for all I between 1 and k. Right? So this is and then if you look at this minimization problem, it is quadratic, right? So you have a square over here. And then the constraint is convex, right? Because each of the fiber to start with is convex. And pass it on to the limit, we say that the P naught belongs to the next stage of the Glaeser refinement if and only if this the solution of this minimization problem as delta goes to 0 will equal to 0. Right, so the punchline is that computing the Glaeser refinement just comes down to computing a quadratic programming problem plus taking a limit. And in practice, this limit will be just some threshold that we are allowed to tolerate. Okay, and I think I'll skip over all of the technicalities and just declare victory over here. Thank you very much for your attention.